All right. Good afternoon, everybody, and welcome to afternoon physics here. Hopefully, you guys are all doing well. And I am ready for another weekend, but it seems like, man, we've just been doing this over and over again. Hopefully, man, I just hope we get all this stuff figured out. Hopefully, when the summer comes, things can get a little bit better, and hopefully, we can come back to school next year in the spring and actually be in school. Without having to have more of this distance learning stuff. But anyway, it is what it is. So hopefully this just all really works out well in the end. Let's go ahead and look through this. I think I only gave you guys a couple problems for your homework. Let me see. I don't remember. I don't think I gave you guys. Did I give you guys number 1? What was it? What was the homework? Yeah, number 1 and 2. So we just skipped number 3. So we're going to look through the homework assignment, and we're going to go through the numbers 1 and 2. And then we're going to look at some new stuff here, all right? And we're going to find that lenses are not hard because they're just like the stuff that we've already done. And then I think, so I have graded all of the tests for a brief moment. So I originally had planned the test to be only 40 points. Then because I remembered that I was including all the sound stuff, that it got a little longer. So the test was 50 points. So sorry if you had like more than 100% on your test, and then you'd be like, wait, all of a sudden your test grade went down. So sorry, for a brief moment, your grade was out of 40 points, but then I adjusted it to out of 50 points. So your grades should all be in on RenWeb in addition to Google Classroom. And if you guys have any questions on that, feel free to ask me. If there's any specific questions that I tell you on Google Classroom, which problems exactly that you got wrong, although I don't have the space to really make a whole lot of comments. So if you want more explanation, feel free to ask me and we can talk about that. Okay, so enough said. Let's jump into the new stuff here. We have, what do we have? We have the angle of refraction for a ray of light that enters a bucket of water from air at an angle of 25 degrees Celsius, or 25 degrees to the normal. And so you want to know what is the angle of refraction for that. All right, so cool. So this is just a very similar situation to what we solved before, right? And so we have just light. It doesn't matter whether it's a bucket of water or it's, going to glass or whatever it is. The only thing that matters is you have two surfaces which have two different indices of refraction. And so here we're going from, from air crossing over to water. Right, and here's going to be our normal, right? So our perpendicular line that we call our normal, and it's entering at an angle of 25 degrees. So kind of like this, that's about 25 degrees. And when we go from an area of low refractive index, so air is N is about equal to 1, water, I think was it 1.33? Yeah. So 1.333. So going from air to water, that the light is going to bend this way. It's going to bend toward the normal, all right? Or it's going to bend inward, all right? And the angle is going to get smaller. Sorry, those didn't connect exactly right, but I think you guys got the idea. And so we're solving for this angle. That's the index of, that's the angle of refraction there for number 1. Okay, and so for number 1, we're going to use Snell's law, where Ni sine theta I equals Nr sine theta R, and we want to solve for the theta R. And so we're going to just go ahead and rearrange this. So you have Ni sine theta I over Nr equals sine theta R, and then we'll just take the inverse sine of whatever we get there at the end. So this is going to be an incident material is just air, so that's going to be 1. And then we have a sine of 25 degrees. And that's going and trying to figure out what this angle is. And so N is, NR is, so Ni, this is NR, is 1.333. Go ahead and plug that into our calculators. And that's going to give us, let's see, the sine, and again, once again, make sure you're in degree mode. Very important that you're in degree mode, because if you're not, your answer will be wrong. Sine of 25, okay, 1 times that, and then we're going to divide by 1.333. That is the sine of our angle, so we're going to take the inverse sine, so that second sine gives you the inverse sine of second answer. So the button down here, so second, and then the little minus sign. And then we hit enter, and that's going to get us 18 point, well, let's just round it to 18.5. 18.5 degrees. Okay, so that is our answer for number 1, 18.5 degrees. Now number 2, the reason I only gave you guys 2 homework problems is because number 2 is actually 3 different parts. We have 3 different parts in number 2. And it's nice because in number 2, one of them we're solving for an angle, one of them we're solving for the material, and the other one we're solving for the angle again. So you get a little bit of, kind of a little bit of variety here for number 2. So this is 1, this is 2. All right, in all of these, we don't need to redraw this diagram every single time. It's nice to have some diagram to kind of remember what's actually happening. And so here we go. So if we have an incoming ray of light of vacuum wavelength 589 nanometers. Fill in the values. And it's important that it says 589 nanometers because that's going to be from, I believe that's the sodium lamp wavelength. But that's the standard wavelength. Because remember, of course, that your index of refraction can actually back to the table earlier. So in A, we have crown glass, and we have from flint glass to crown glass. So we have from one glass to another glass. So for all of these, we're going to be using Snell's law. And for all of them, we're going to end up essentially with this equation, right? And so that's going to be your sine theta r equals ni sine theta I over nr. And let's go ahead and put in some numbers. So in this case, your initial angle for 2a, we're solving 2a first. For 2a, it's what? 25 degrees, once again. And your initial index of refraction is what? That's for going from a flint glass to crown glass. And so flint glass, I believe that's 1.66. Okay, so you guys can look back in your table. I'm not going to keep on going back and forth because then I'll lose these problems here. But it should be, your Ni should be 1.66, which is the index of refraction for flint glass. Flint glass has some more dense material in it, which is why it's larger than ordinary glass. Okay, so 1.66, and we have an angle of incidence of 25 degrees. And then this is going to be over crown glass, has an index of refraction, so it's going into crown glass, which means that's, let me look that up real quick. So that's 1.52, okay? So let's go ahead and calculate that. 1.66 sine of 25 divided by 1.52. And that gets us this. Remember, this is not the angle, but this is sine of the angle. So if we want the angle, we're going to need to do the inverse sine of that. And that gets us 27.5 degrees. Now let's think about that for a minute. So 27.5 degrees. And think about, is that correct? Does that make sense? Right? We're going from 25 and the angle is getting bigger. Well, does that make sense? Yes, because it's going from an index of refraction that's high to an index of refraction that's relatively low. So going from high to low, we expect the light to actually have a larger angle of refraction. It's going to bend away from the normal in that case when it goes from a high to low index of refraction. Secondly, we notice 27.5 is very close to 25. Those numbers aren't that different. And that's also going to make sense because flint glass and crown glass are fairly similar. they're not, you know, you're not going to expect a big difference for those two. And so because you're not going to expect a big difference, we're not surprised that the angle is not going to be that different. So this makes sense, all right? Make sure your answers make sense. It's important for them to be reasonable. B. All right, in this one, we actually have both of the angles, but we don't have the medium. So what does that mean? That means we need to solve for your NR, your index of refraction of the material that it's going into. So it's coming from air going into something else. So let's go ahead and write out the equation and solve for NR in this case. So it's going to be NI sine theta I equals NR sine theta R. In this case, solving for this, so we're going to divide both sides of the equation by sine theta R. That's going to get us NR equals NI sine theta I divided by sine theta R. Let's plug in some numbers. So NI, we know air, once again, that's just going to be 1. And it's coming from an incident angle of 14.5 degrees. And on the bottom, so it's going to bend toward the normal, and so we get an angle of 9.8 degrees. And let's see what that is. Okay. So that's going to be, so 1, we can just ignore the 1. That's going to be your sine of 14.5 divided by sine of 9.8. Oops, and I made a mistake here. So be careful about this. I didn't close the parentheses. That's going to be pretty important. It's going to mess everything up if I don't close those parentheses. Normally you don't need to, but if you're going to do a complex thing like this, you need to make sure you do that. So sine 14.5, and then close the parentheses, and then you're going to divide by a sine of 9.8. And so we're good now. Okay? And we got 1.47 equals 1.47. And for this one, you're not going to obviously remember any of these index of refractions. But what you just do is you go back into the table and you look, you know, what's close to 1.47. And I think it said glycerin for this one. I think that was what it was closest to, 1.47. I don't know if there were any other possibilities. I don't have the table in front of me right now, but when I did it before, I got glycerin. So 1.47 should be glycerin. The key thing is that you're getting this right. Okay? All right, C. All right, last one here. We have diamond as one of the mediums. All right, so going from air to diamond, so you're expecting now a big change. Because going from air to diamond, and diamond's over 2 and air is just 1, okay? So here we're solving for the angle. And so once again, we're going to use the same equation that we used up here before, and that's going to be your sine of this refracted angle is going to be equal to NI sine of your incident angle over NR. And if we're starting off with air, this is just simply 1. And this is going to be sine of 31.6 degrees. And we're going to divide by the index of refraction of diamond. And like once again, that's going to be a really big number. So what is that? That is 2.419, I believe. 2.419. Almost 2.5, right? So 2.419. And let's see what we come up with. So sine of 31.6 divided by 2.419. And it gives me that number. Now that, of course, is not the angle, but we're going to take the inverse sine of that number and come up with 12.5. 12.5 degrees is a lot smaller than your incident angle of 31.6. But that makes sense because you're going from air to diamond, so a big difference, and that's going to be a lot smaller. Should it be smaller? Yes, indeed it should be smaller because it's going from a low index of refraction to a high index of refraction, so it's going to bend toward the middle. It's going to bend toward the normal in that case. Okay? So that's your homework, guys. Any questions on that? I think I didn't assign number 3. It's just 1 and 2. Okay? Any questions? All right. Hopefully we're going to be able to end early today. It's a Friday. That'd be nice. Although the new material will take a little bit of time to go through to get into lenses. Although it shouldn't be too difficult, so we don't need to go too slowly through it, simply because lenses are honestly a lot like your mirrors. The diagrams are done more or less the same way, and the equations are the same. The only difference, there's only real difference, is that light is going through rather than bouncing back, and that's going to be the only real difference. So it's going to be a little bit different in terms of what's negative and what's positive, but it should make sense. So if you guys don't have any questions on this, we're just going to jump right into the new stuff, if you guys don't mind. All right. And Adam, so I hear you're winning your chess division, right? And then everybody in my division is deciding to just like give up their queens to me, which is perfectly okay with me. All right. So far, Jason and I, all right, you guys are almost done. All right. Yeah, he lost, wait, oh, both queens you mean for both games. Wow. Well, I haven't had that happen. I've just had 2 different people lose their queen to me, but not on both games. That would be crazy. I guess people don't like their queens. They're just like, no, I just want to be a king myself. I don't want a queen. That's weird. I like my queen. All right. Sometimes I even try to, well, yeah, I'm gonna leave it at that. All right. So we're gonna talk about some lenses today. Lenses. And they are a lot like mirrors, which is kind of interesting that they're so much like mirrors, because in all honesty, they work different ways, right? Mirrors reflect light. Lenses work by refraction, right? They work through the bending of light. And that goes through these equations using sines and all that kind of stuff. Whereas in a mirror, the light simply just bounces back at exactly the same angle. So you kind of think that, man, they should be different. They should be a lot different. But it turns out that they're not. They're very, very similar, which is what I like. And you guys should enjoy it too. And so let's go through some equations. All right. Our first equation that you may recognize is 1 over P plus 1 over Q equals what? 1 over F. The same. The lens equation is the same as the mirror equation. That's pretty awesome, right? And guess what? Your magnification equation is the same, right? It's still going to be the H image over H object equals negative Q over P. The same. Your equations are the same. Okay? What's going to be different is here, let's just go through some, you know what? The easiest way to do this is to actually go through sample problem. Well, I don't know why I closed my book. Let me open this back up again. And so let's go through a sample problem for our lenses, and we'll look at how these actually appear. And so we can do the equations, and we can go through the drawings. The drawings are going to be very, very similar. But rather than just make up a drawing, let me actually go to a sample problem and look at that. Okay? So that's going to be the easiest way, in my opinion. All right. So we have an object here in our sample problem B on page 797. Is placed in, let me see, 30 centimeters in front of a converging lens, and then 12.5 centimeters in front of a diverging lens. Both have a focal length of 10 centimeters. For both cases, find the image distance and describe the magnification. And describe the images. Sorry about that. All right, so let's see what is going on here. So we have 2 different situations. We've got a converging lens and a diverging lens. Okay, so a converging lens is, is actually going to look like, actually let's move this back a little bit more. A converging lens is going to look like this, okay? And it's also called a convex lens, which is interesting and opposite of the mirrors. If you recall, a convex mirror is a diverging mirror. Here, a convex lens is a converging mirror. A convex lens is a converging lens. Okay, so let's recall. So it's similar to, this is a, and so here's your object over here. And if this is a mirror, a concave mirror is a converging mirror. In general, it's a converging mirror, although of course it's able to make virtual images also. It's a converging mirror, right? So a different, that whole concept of what's convex and what's concave has to do with the shape of the object and less to do with how it interacts with light, okay? So a convex lens is a converging lens, whereas a concave mirror is a converging mirror. These two things, these two are very, very similar to each other, even though their names are different. A convex lens is like a concave mirror. A convex lens is like a concave mirror, okay? And then the same thing is true about your diverging lens. Your diverging lens is going to be your concave lens, all right? But we'll get to that here in a minute. So in your lens, you have a center and you have a focal point. However, it's a little bit different from your mirror, right? Your mirror, your center is going to be right in, you can imagine that the mirror is one sphere and the center is the center of that sphere. And then the focal point is going to be halfway in between the center and the end. Well, it's a little bit different for a lens. In a lens, your center is, well, right there in the center of the lens. Here's your center. And you do have a focal point too, right? Only this time, the focal point, and this is another place where it's going to be different, okay? So let's suppose we have an object that's over here, okay? Because your light for a lens is going to be going through the lens, all right? So it's going through the lens, your focal point is going to be over here. It's going to be on the other side of the lens, okay? So if it's coming in parallel, once again, it's going to go through the focal point like that, okay? And so what you're going to notice that unlike the mirrors, this over here, and this is what's super important to keep in mind, this over here is positive P, right? P is always positive because that object is going to be a real object. You don't have a virtual object. Virtual objects are not real. That's the whole point of something being an object, right? But your image can be virtual or real, okay? And so over here is going to be, this is going to be positive Q. So your Q is on the other side of the lens. Well, why is that? Because the light is going through the lens, and this is where the light is, and so this is going to be where your real image is. Okay, your real image is on the other side of the lens, not the same side as the object. It is, you might ask, is it possible to have an image on the same side as the object? And yes, if you have an image on the same side as the object, that image is virtual, and your Q is negative over here. So this is positive P or negative Q space. So that's a little bit different, okay? So remember, for a mirror, when the image was on the opposite side of the mirror, that would be a negative value. But in this case, when the image is on the opposite side of the lens, that's going to be a positive Q, and that's going to be where your real image is. So we still say that positive Q is a real image, it's just the location of that image is different. So the equations are all still the same. The meaning of a negative Q being a virtual image is still the same. The only thing that's different is the location of your Q. Positive Q on the opposite side of the lens, okay? The other thing that's opposite is this whole converging, diverging thing, okay? But that's just terminology, which is not as important. The positive, negative is more important. Positive Q on the opposite side of the lens. Okay, so armed with that, okay, and also one more thing, what in the world does focal length actually mean? How do we define the focal point or the focal length? The focal length, and you can get this, let me see. So focal length is the image distance. So if you have like an image that's in focus, the image distance for an infinite object distance. Well, why do you need to use that? No, obviously we're not going to have any kind of infinities here, but infinite typically can be, you know, if something's 20 feet away, that's pretty close to infinite, okay? For lenses, okay? So something might be 20 feet away, and then you get an image that's only, let's say, 10 centimeters from the lens itself. That would be a 10 centimeter focal length, okay? So we're going to define, rather than defining the focal point or the focal length in terms of the radius of some particular mirror, something like that, the focal length, because it depends on the shape of this and it also depends on the material of this, we have no real way of having a very good correlation between the focal length and the shape, right? Because it also depends on the material, the index of refraction, all that kind of stuff. So it gets a little messy. So we're just going to define the focal length as, okay, the focal length is going to be the image distance for an infinitely far away object. But of course, we can approximate things that are fairly far away, like 20 feet away, as infinite, even though it's not really infinite. Why do we need infinite? It's infinite simply because we need parallel lines. You have parallel light comes through, and when it comes through the lens, it goes through the focal point. Okay, so enough of that. Let's actually solve this problem here. So let's come back to this problem. We have sample problem B, and let's solve it. And we're going to go ahead and say, we're going to do first a converging lens. Converging lens is going to be a convex lens, and it's going to be 30 centimeters in front. All right, let's do the math first, okay? So 30 centimeters, that's going to be in this case, your P is going to be 30 centimeters. You don't know where the image is, right? So we want to find, so your Q, you don't know that for this, okay? So P is 30, Q is, I don't know, and we have a focal length of 10. So F equals 10. This is for your converging or convex lens, okay? So we have the same equation. Let's go ahead and solve it. So 1 over P, let's just write it. 1 over P plus 1 over Q equals 1 over F. So we have 1 over 30 plus 1 over Q equals 1 over 10. In this case, and very importantly, 10 is, and this is 10 centimeters, 10 is positive, right? Why is it positive? It's positive because this is a converging lens. Converging lens means that it takes the whole idea of what is converging. It means it takes the light and focuses them into a point. And we're going to see what how a diverging lens works in the opposite way. Okay? So because it's converging, F is going to be positive. All right. So next up, let's go ahead and do the calculation here. We have 1 over 10. We're going to subtract 1 over 30 from that, which is going to be, no, it's going to be 2 over 30s. Anyway, 1 over 10 minus 1 over 30 is going to be this. And then we're just going to take the inverse of that by doing x to the minus 1. And let's get that answer. Is f always positive for a converging lens? Yes. F is always positive for a converging lens and always negative for a diverging lens. Always, always, always. Very important. Okay, so we got Q is 15. Don't forget your units, right? They don't have to be centimeters. They might be meters, they might be inches, they might be feet, but I think almost everything we're dealing with here is in centimeters. So in this case, Q is 15 centimeters. Don't forget your units. People did lose some points in the test for forgetting their units. It's so, so sad when that happens, but it inevitably happens every single test. I don't know why, but it always happens. So it's 15 centimeters. Our M, we can go ahead and calculate M is going to be negative Q over P, and that's going to be negative 15 centimeters over what was over 30 centimeters. So that's negative. All right, looks like we had some more technical issues. We're going to go ahead and draw this as best as we can. And so we're going to make a little principal axis in this case. And we're going to go ahead and draw a lens here. All right, this is the center of our lens, and we have an object. Let's go ahead and place it over here. So 30 centimeters away, so we can just go ahead. Let me see, where's my ruler is like upside down here. All right, so we have our focal point is 10, and then it's going to be 10. And our object is 30 centimeters away. Just right there. There's our object. Okay. So we have two focal points. You don't actually have to write them both. You just need the focal point over here. Unless, well, sometimes you do actually need both of, or one of the other focal points. So we've got some object here. Don't care what the object is. I draw trees because I like trees. All right, so there we got our tree, and we're going to do the same kind of thing that we did before, okay? The light now is going to the other side, and so once again, the same kind of method for drawing these is going to work. All right, light is coming in parallel. It's going to go out through the focal point, okay? So light's coming in, and then drawing these things can be tricky sometimes. So stop right when you get to the middle of the lens, and then we're going to go through the lens and go to the focal point. This thing is quite, has a very, very small focal length, so it's bending the light quite a bit. For a converging lens, the light bends in, okay? And we can also say that if it goes through the center, it's going to go straight through. Remember, for a mirror, we said when it goes through the center of the mirror, it bounces back through the center. Now, all we say is when it goes through the center, it just goes straight through without bending. And that's the way refraction works, that it's just going to go through the center, straight through. And that's it. Those are our two lines, okay? Where those two lines cross is going to be where the image is. And let's check this out. This is going to be where our image is. Look at this. It's upside down. Let's see if that makes sense. We have a magnification of -1/2. Remember that negative means, the negative means it's inverted or upside down. Right? That's what the negative means. And the 1/2 means it's half the size. That looks like about half the size to me. And let's see if our Q makes sense. This right here, the focal length is 10, and this is a little bit further, which is 15. 15 makes sense. Notice here, guys, positive is on the opposite side of the lens, which is what we see here. This is our real image. So this is the image is real, it's inverted, and it's smaller. Okay, so that's how we would describe that image. All right, it's real. How is it real? If I had a piece of paper there, I could have the image on the piece of paper or a screen or anything else. So you could see it on this, you could not only if you put your eye there would you see it, but also if you put a screen there or a piece of paper there, you would see that image reflected on that. Okay, so that's not the case for a virtual image. All right, virtual image is only just something that you see with your eye by looking on this side and you see an image over here. All right, so that is your convex lens. Let's go ahead and do, I said we're going to finish early. We're not going to finish early. I should have known because I have to do two sample problems. One for the convex lens and one for the concave lens. And a concave lens is a diverging lens. Diverging. And it's diverging because the light, when it comes to the lens, it goes out. And a diverging lens is what your glasses are made out of if you are nearsighted. All right, so if you have myopia and you're nearsighted, your glasses lenses are all diverging lenses. All right, so question. So the real virtual image is still dependent on the sign. Yes. Yeah, exactly. So if Q is positive, it's still real. If the M is negative, it's still inverted. So those things have all exactly the same meanings. The only difference is it's flipped as to which side is positive, which side is negative. But otherwise, it's the same. All right, let's go ahead and do the last example here for a diverging lens. And that is, in this time, let me see, what do we got? What do we got? We have an object that's placed 12.5, so P here is 12.5 centimeters in front of a diverging lens. And both things have a focal length of 10, but in reality, because it's a diverging lens, this is going to be negative 10 centimeters, right? Negative because it's diverging. Diverging is F is always negative. Okay? So F is negative if it's a diverging lens, and that's because it's going to be spreading out. All right, so let's do some calculations. We have the same equations, 1 over P plus, you know what, let's just plug in some numbers. Right, we have 1 over 12.5 plus 1 over Q equals 1 over negative 10, and so it looks like we're going to get a negative number out of this. Right, so 1 over negative 10 minus 1 over 12.5. We're going to get a negative number there. Take the inverse of that, and it's going to be a negative number as well. Negative 5.56. Q equals negative 5.56 centimeters. And once again, it looks like I'm going to get a smaller object. Okay, so we can calculate M is negative Q over P, and that's going to be negative of a negative is a positive, so that's going to be 5.56 over P is 12.5. So take this, divide by 12.5, and I'm going to get, and remember it's the negative of this, so it's 0.4444, so it's a little bit less than half. So 0.44, so the magnification is going to make this smaller. So this is also going to be smaller. Let's go ahead and draw this particular lens, and then we'll be all done. And in this case, we can, you know what, we can just continue this principal axis over here. Now our diverging lens is going to look a little bit different. It's going to look like this, and you don't have to get these things drawn accurately completely. All right, but your diverging lens is going to look like this. So it's thin in the middle and thick here at the ends. Again, this kind of like what your lenses look like if you are nearsighted. Okay, and so what that's going to do is when light's going to come in there, instead of focusing it in, it's going to spread it out. Right, and you say, okay, well, how do I know how it spreads out? Because you have a focal point on both sides. All right, and so let's go ahead and do the math or do the drawing here. So we have a focal length of 10 and then distance of 12. You know what? I'm gonna spread this out a little bit more. So rather than doing 10, let's make this let's make this 20. Let's just double everything. And then the object is at 12.5, so that's just going to be 25. And then this over here is just going to be 10 also, which I'll put right there. Okay, so this here is the center of the lens. Here's a focal point. Here's the other focal point, and here is my object. Let's do that. All right, let's make a tree, because trees are awesome. All right, and maybe I made the tree a little bit too big, but whatever. No problem. And once again, when it comes in parallel, it's going to go out through the focal point. So let's try to make that parallel line, kind of like that. That looks parallel-ish. All right, light's coming in. Once it hits here, remember, a diverging lens is going to make the light go out, okay, not in. And so how's it going to go out? It's going to go out as though it were coming from this focal point. All right, so what you're going to need to do is, this is the virtual light. There's no light over here, but that's the virtual light. And then the light is going to go through the lens over this way. So the diverging lens takes that light and makes it go out. That's how it's diverging. All right, and then of course, going through the center is the absolute easiest thing to do. So I'm going to go ahead and go to the top of the tree, then go through the center, and then that's it. But of course, remember, the light is coming from this way, so this is both real light coming from the real side, and it's virtual for after it goes to the other side, okay? So where do those two things cross? They cross only on the same side as the image itself, or as the object itself. So the image and the object are on the same side of the lens, which means that this is a virtual image because it's on the same side as the object. And so let's see if our numbers make sense. 0.44, it's positive, which means this is your M. When your M is positive, it means the object, or the image is upright. Positive M is an upright image, and 0.44 means it's smaller, right? So it's about half the size, a little bit less than half. That looks like kind of half-ish, okay? You know, more or less half, right? And if Q is negative, that means that's a virtual, which we get virtual when they're on the same side as, when the image is on the same side as the object, and it's also smaller. We said smaller already. Okay, so that's it. That's your lenses, your converging lenses, your diverging lenses. Everything is very, very similar to the mirrors. Just keep in mind the differences, and then you'll be good to go. All right, hopefully you guys enjoy this. I really enjoy drawing trees like this, and hopefully you guys enjoy it too. All right, have a great weekend. I'm going to go close out here. I think I'm losing people already, which is perfectly fine. All right, any questions before I sign out? What's the homework? Oh, I haven't uploaded or updated that yet. The homework is, it's going to be 14B 1 to 3, and then 4A and C. Okay? So 1 to 4, but problem 4 is only A and C. Okay? So 14B, which is right here, problems 1 to 3, and then 4A and C. And I'll go ahead and put that up right away. All right. See you guys.